Log on, tune in, find out. Another good idea from Cambridge.
Today is Indranil Biswas, who will speak on orthogonal and symplectic parabolic bundles.
Okay. Let me first thank the organizers for the invitation. So, this is a report of some joint work with Swaradip Majumdar and Michael Lennox Wang. Okay, so parabolic vector bundles are introduced by Mehta and Seshadri. So, they constructed the moduli and also most importantly they showed that the parabolic bundles correspond to unitary representations of the open Riemann surface, but there everything was done in terms of assuming that all the weights are rational. So, that means the local monodromies are all finite order. So, subsequently it was generalized to all real weights by Simpson, Picard, Porridge, etc. These people independently did it. So, then the question came for principal bundles. So, it was done for example by Telemann and Woodward did it, then Balaji Nagaraj and I also did it about principal bundles, but about principal bundles all work done so far are the analog of rational weights. So, there is no, so people have not handled irrational weights in the case of principal bundles so far. So, we to consider the special case, so orthogonal and symplectic bundles. Okay. So, let us first recall what is a parabolic bundle. X is a compact Riemann surface S we fix a finite subset x1 x2 xn fix finite subset E over x, a holomorphic vector bundle So, let us recall a quasi parabolic structure on E over S is a filtration EXI. So, filtration of the subspaces of this of the fiber, this is a quasi for all xi. This is a definition of quasi parabolic filtration. So, a parabolic structure on E is a quasi parabolic filtration as above. structure together with parabolic wires, together with real numbers between 0 and 1 for all. So these are called parabolic wires. This, note that this exactly correspond to the quasi-parabolic filtration. So alpha ij is the weight of Fij. So now with this notation, parabolic degree, let us recall. So the entire data, namely E with quasi-parabolic filtration and parabolic wires, let's denote it by E star. The data as a parabolic degree of E star is defined to be degree of the vector bundle plus summation I is equal to 1 to n this point, and j is equal to 1 to ai, that index alpha ij times the dimension f ij quotient f ij plus 1. So this is defined to be the parabolic degree. And parabolic slope mu parabolic of S star is equal to parabolic degree of S star by rank of it. Now note that if E is a, let F be a holomorphic subbundle, note that F has an induced parabolic structure which is defined in obvious way, namely you can take the filtration of f xi exi and intersect with filtration of this and intersect with the subset the subspace f xi. So that way you get a filtration of, let's take the subspace of exi given by that. Now maybe it's a bad notation. F, maybe let me call it V. Vxi. You take the subspaces of Exi and intersect with Vxi, so you get a filtration of the fiber Vxi and you give the appropriate weights. So it has of course a induced parabolic structure. Now E star is called parabolic stable, respectively semi-stable. If mu para v star is less than or equal to mu para v star. Okay, so by v star I denote the induced parabolic bundle. V star is defined to be the corresponding parabolic vector bundle. Respectively, mu para v star is less than or equal to mu para v star for all sub bundle V with rank of V is positive and less than of rank of, strictly less than rank of V. So this inequality should hold for all subbundles with this property. So then it's called parabolic stable or respective semi-stable. Yep. Now another notation definition: E star is called parabolic polystable if it is semi-stable and direct sum of stable parabolic bundles. Since it is semi-stable and direct sum, it automatically means that it is equivalent to saying that it is a direct sum of stables of same parabolic slope.
Have you defined the direct sum of parabolic bundles?
Yeah, that's obvious. So namely, you take the direct sum of the underlying vector bundles and the direct sum of the flags.
How do you do a direct sum of the flags?
Yeah, okay.
Are
So,
there ways of ordering them?
yeah, no, because it comes with the weight, no parabolic weight. So that's give you the ordering.
So you have to order them. You use parabolic ways. To
Yeah, of course.
The order.
Yeah, of course,
Okay.
of course.
So it does. It's not purely dependent on the quasi-parabolic.
No. Of course not. No.
It does really use
Yeah,
the weight.
yeah. Because if we shift the parabolic weights, it will change completely. Because, yeah. Of course. Yeah, good point. Yeah. The quasi-parabolic structure, I should emphasize what you just now said. Quasi-parabolic structure of the direct sum is not just a function of the quasi-parabolic structure of the individual. It depends on the parabolic weights. Okay. So I have defined polystable. Okay, now I can state the theorem which I mentioned before, Mehta Seshadri and Bicard for it Simpson. So I'll give a rough statement. isomorphism classes of polystable parabolic vector bundles of parabolic degree 0 are in bijective correspondence with parabolic vector of rank n, let's fix here, of rank n, a parabolic degree with home pi 1 of x minus s un quotiented by un conjugation and the polystable corresponds to polystable of rank n and degree 0 correspond to this, and stable ones correspond to this irreducible representation home pi 1 x minus s un irreducible. This even is the conjugation action, of course, so which acts on the representation space, homomorphism space. So, and this correspondence this correspondence. What is this correspondence? This correspondence is what is called Delil extension. So, given a local system and a choice of the log of the monodromy, so you can there is a natural extension which was constructed by Delin many years back. So, this is just text, the correspondence is Delin extension. It's Delin extension. So, I said that this is a rough statement because this is the actual statement is finer than this. That is equivalence of categories, not just bijection, because what it means is that if when you have a homomorphism of parabolic vector bundles of degree 0, this is automatically flat. So, the homomorphisms which is not captured, that aspect, if I just say bijective, it is actually equivalence of categories. So, extra statement which is there, but it is not is not this in because I said it is rough version. The rough version does not say is that homomorphisms are actually homomorphisms, and homomorphisms of parabolic vector bundles of degree 0 actually flat. So, it is compatible with the representation. So, actual statement is equivalence of categories. But it is easier to state in a bijection. Anyway, so next one can define just as dual of parabolic with vector bundle tensor product of vector bundles, one can make it define it for parabolic dual, parabolic tensor product and parabolic homomorphism. We will define, actually we will not give the definition, but I mean just explain what they are. Define parabolic dual parabolic tensor product. In parabolic homomorphism. Okay. So, how it should work, this is clear from this theorem, namely parabolic dual should be correspond to the dual of the representation, parabolic tensor product should correspond to tensor product of representations, and homomorphism bundle should correspond to the representation to the home space. That means you have a Cn and Cm, you have action, so then you take the induced action. So construct using this action, you construct the homomorphism bundle. So that's how in principle it should be defined, and that's how it is done. But if I have to write down the actual definition, it will be a bit cumbersome, but what is happening is very clear. So how it is defined. So let me say one more way to define, which is basically again the same thing, but I said that parabolic vector bundles I earlier mentioned parabolic vector bundles and with rational weights and or parabolic principal bundles. Actually, they are all bundles on the usual bundles on the Deligne-Mumford curve. So earlier people did so now that language of stacks is now universally accepted. So if you have a principal bundle or a vector bundle on a smooth Deligne-Mumford curve, suppose you have the map to the coarse moduli space, which is a compact Riemann surface. So you maybe I should have said this at the beginning. So your parabolic bundle is basically just instead of looking at bundle on this, you try to look at on this and just keep track of extra whatever data is needed, so that you can whenever you want you can get it back. I mean, so it's nothing more than that. Parabolic bundle is. So from that point of view, all these are just usual operations. See, I can take the dual of a vector bundle on this tensor product or homomorphism. So whatever it translates to is that's the parabolic construction.
But isn't there some equivalence between? Don't you have to introduce some equivalence on these things? Don't you need to introduce some equivalence on these things?
Equivalence of?
Equivalence on pairs consisting of a Deligne-Mumford curve and a vector bundle.
Yeah, just usual isomorphism, not even equivalence.
What if you have a stacky point of order 2, a stacky point of order 4?
Yeah, that will correspond to parabolic structure on that. Yeah, exactly. That's exactly.
Well,
yeah. Yeah, that's exactly the that's exactly the stacky points will be image of the stacky points will be exactly the parabolic points.
I don't understand that. We'll talk about it next.
Yeah, okay, we can discuss it. But yeah, but is it yeah. So the parabolic, as I said, all these operations are just operations here, and you translate that operation, so you get the okay. Now let me define orthogonal and symplectic bundles. Okay, so parabolic orthogonal model. So for that you fix a parabolic line model. So orthogonal structure is given by a homomorphism of parabolic bundles. So this is a parabolic tensor product and the homomorphism such that the following conditions hold, such that it is symmetric. Let us call it phi. Symmetric and then you can do the following thing, and I will explain another condition, and the following holds. I will explain the condition. So you can tensor both sides by the parabolic dual. Now E star sits inside this as E star tensor alpha going to alpha tensor identity. Because these are parabolic homomorphism bundles, endomorphism bundles, so identity map is there. So I should have just said one thing which I forgot, I should have said. So of course, by construction, the way I have defined, it is obvious that the usual identity holds, namely E star tensor E, parabolic tensor E star tensor F is equal to home, parabolic home. Let me write it clearly. Home model. So here the identity map is there. So you have you can consider the composition. The condition is that the composition is an isomorphism. So this is as you can easily understand that this is equivalent to the non-degeneracy condition, but since it is a parabolic tensor product, I mean one has to be slightly, it is not I mean this is the quickest way to saying non-degeneracy. You can also say directly, but I mean it will become a bit messy. So now once you have defined orthogonal bundles, symplectic bundles are also obvious now. Parabolic symplectic bundles. So
Indranil, I think that E star down there on the bottom right should be E star dual.
yeah, no here.
Yes.
This one, yeah. Yeah, that's it, thanks. So, condition is a skew symmetric. Plus the same condition, namely composition is an isomorphism. These are requirements. So, if you forget the parabolic structure, then in the usual case, of course, this coincides with the usual definitions of. And note that orthogonal and symplectic, when I am saying the bundle, this is not, these are not SP or SO bundles, but rather GP or GO bundles with similitude group, because I am not fixing this line bundle to be trivial. So, it is a, so that is why it is a. So, symplectic SP or SO bundles will correspond to when this is a line bundle is a parabolic line bundle is trivial. That means trivial line bundle with 0 parabolic weight. Okay. So now I am to define connection on principal these bundles. So, we can define connection. Well, I should specify that my connection, I mean algebraic connection to begin with. We will connect or holomorphic connection, same thing, but we C infinity connection we will consider later. For the time being, this is only holomorphic connection. So, okay, let us recall the definition of logarithmic connection here. So, first connection on parabolic bundle. So, as before we have this E. You recall that a logarithmic connection singular over the divisor, what was the notation? S or D something, yes. is a differential, holomorphic differential operator. Holomorphic differential operator. Satisfying Leibniz. So you K is the canonical bundle, holomorphic cotangent bundle. Since we are working over Riemann surface, things are slightly simple, so I can just put here, otherwise one has to take the logarithmic forms. So connection on the parabolic bundle is as follows, says that, and let us recall what is residue quickly. So take any point residue at a point xi in S. So if you restrict the point, everything to the point, these two bundles, they are just dual of each other, because it's the Poincare residue formula, it's the normal bundle which is tangent bundle, so it gets cancelled off. So now the composition is OX linear. Composition is a endomorphism. This is OX linear. So you get M. So you get an element of and linear endomorphism. This is called the residue. Residue of D at xi. So a parabolic connection on a parabolic vector bundle is a logarithmic connection, but it has to have some compatibility property with the quasi-parabolic filtration and the parabolic weights, which I will define. So this is the definition of a logarithmic connection. So now I am to define a connection on a parabolic vector bundle. So condition is, it is denoted by residue B at xi, B of the connection D at the point xi. So the condition is that a connection on parabolic vector bundle is that the conditions are first condition is that residue of B at xi on Fij. You remember the quasi-parabolic flag, so this should go into, of course, that's natural to expect, it should preserve the quasi-parabolic filtration, but that's not enough. You need another condition, that it should be the compatible with the, so that with the weights, namely residue B of xi. So on Fij quotiented by Fij plus 1. So now this makes sense because it preserves the filtration, so this residue gives endomorphism of the grade A object. So this should be alpha ij times identity of this vector space, namely Fij by Fij plus 1. So the condition is that it should preserve the quasi-parabolic filtration, and on each graded piece it acts as the scalar multiplication by the parabolic weight. So this is the definition of a connection on a parabolic bundle. Now I want to define a connection on orthogonal and symplectic bundles. So for that, first you have to fix a connection on L, parabolic line bundle. Fix a connection on L star. I have already defined connection, so this is a parabolic line bundle, so this is the connection. But here the first problem occurs, but I will not, it may not have a connection. So the necessary and sufficient condition, that is parabolic degree 0. So I should add a comment here. A parabolic vector bundle if a parabolic vector bundle V star has a connection then parabolic degree of V star is equal to 0. So when I say fix a connection on L star, that means that I am assuming that L star is of parabolic degrees, otherwise there is no such connection. And of course, by connection, as I should emphasize that as I beginning I said algebraic connection. So these statements of course are not true for C infinity connection. Now, how one should define is very obvious, because let D be a connection on this parabolic vector bundle E star. Maybe I can just write it here because it is easier to let D be a connection on E star. It will induce a connection on this, and this has we already fixed a connection on here. So this has a connection using it and DL is the connection fixed on L. Using the connection on E star and L star, we get a connection on this dual tensor. D will give a connection on the dual vector parabolic vector bundle, and we have a connection already given a connection on this, and just as usual, the tensor product, if you have two individual bundles and connection, then the tensor parabolic tensor product gets a induced connection. Using it and DL, this bundle E star tensor L star gets a connection. So now the requirement is obvious. This map should be isomorphism. Map should be, this isomorphism should be connection preserving. The requirement is that is an isomorphism. So for the connection, preserving connection. Similarly, orthogonal case also, a symplectic case. You have a connection on this, so you get a, if you have a connection on E star, you get a connection here, and so the connection on L and together get a connection here, and DL is a symplectic DE. The connection DE is a symplectic. It's called symplectic. If the isomorphism is connection preserving. So, it is a connection on the usual parabolic vector bundle together with the extra condition that this isomorphism is connection preserving. But for that, as I emphasize, for that you have to fix a connection on the line bundle. So, everything is tied to that. Okay, now for a principal bundle, usual principal bundles, you know that the connection space of connections is an affine space for the holomorphic one forms with values in the adjoint bundle H naught of add E tensor K. So, let us see what is the corresponding vector space for which the space of connection is an affine space. Suppose, so let us take first the case of say orthogonal case. The symplectic case is very similar. So, suppose T is a locally defined section of some parabolic that means locally defined section of E star star tensor E star. Now, suppose we put the condition, this is the isomorphism phi, this is homomorphism phi. So, I will define add E star phi to be this endomorphism bundle. I have to define this, define with the following condition: T lies here if phi of T lies here lies in add E star phi if phi of is equal to 0. So, I have the parabolic endomorphism bundles. I am to define a subbundle parabolic subbundle. So, a section we locally defined section is of here which lies in the subbundle if and only if the condition is that this is 0. So, this is contained here by definition. So, this endomorphism preserves the flag, and for the parabolic point the endomorphism has to preserve the flag, because any section here by definition preserves the flag. This parabolic endomorphism has to preserve the flag. So, this is not the usual tensor product. So, it is the parabolic tensor product section here will automatically preserve the flag because the parabolic endomorphism. So, it preserves the flag. So, now here a subbundle, I mean subshift, not subbundle. Subshift defined by the property that nilpotent on the flags. With respect to the quasi-parabolic filtrations. So this, so let me again go through the definition. This one can see that this parabolic and homomorphism bundle is a sheaf of homomorphism with underlying vector bundle preserving the quasi-parabolic flag. And then I have defined the sub-object of this, namely putting the extra condition that this holds. It compatible with the phi. This is the compatibility condition. And then after defining this, I am defining another subsheaf of this with the condition that it is nilpotent with respect to the flag. So, it is here only flag preserving, but here it is nilpotent with respect to flag. So, I am running out of time. Now, I will just make a statement that needs some explanation, but connections on is orthogonal or symplectic case is an affine space. The space of connections on this is an affine space for the vector space H naught x x tensor O axis. This is an affine space, and this behaves like the adjoint bundle, and this is basically this Ax is the corresponding set dual object. This is the adjoint bundle. This tensor Kx tensor Ox in the parabolic category is a set dual bundle. In particular, what I mean is that add not E phi tensor OXS is star. they are canonical isomorphic. Anyway, I don't have time. I will not go through it. Any more explanation of this adjoint bundle? So now I will state a theorem before it is too late. Theorem. A parabolic symplectic bundle if I admits an algebraic connection if and only if for every parabolic vector bundle V star says that for every parabolic V star says that this is isomorphic to V star direct sum V star tensor L direct sum. I will put a bracket here, I will explain why I am putting W star where maybe I should express the sentences slightly differently. For a parabolic, for every parabolic V star such that there exists a symplectic parabolic bundle W star P W such that I should have E star direct sum W star P. Note that this is a, let me send complete exercise that so for every parabolic vector bundle V star such that there exists a symplectic vector bundle W star phi W with these two are isomorphic. This is a symplectic bundle. W star phi W is a symplectic bundle as you all. Now V star direct sum V star dual tensor L that has a natural symplectic structure, because just as any vector bundle V star tensor L has a natural symplectic pairing with values in L. So this has a natural symplectic pairing because I have put the dual here direct sum. So for this condition should hold. That is the this is the necessary and sufficient condition. And for orthogonal case, the theorem is exactly similar, except just as here there is symmetric pairing, there is also a skew symmetric pairing. So you can just say that instead of phi s, you should take the orthogonal one, symmetric one, that phi o. This should hold. So this is the statement of the theorem. Maybe my time is over actually, so maybe I have to stop. I wanted to say something about infinity connections, about Hermitian Einstein. Yes, okay. But anyway, it's not time for. I'll stop here. Thank you.
Any questions?
Is there a relation